Industrial manufacturing faces a constant, unforgiving problem: how to synchronize the physical output of a factory floor with the unpredictable desires of the market. To bridge the gap between internal production and external consumption, lean methodology relies on a single definitive metric known as takt time. Takt time dictates the maximum allowable time a system has to produce one unit. It does not measure the top speed a machine can achieve. It calculates the exact pace the system must maintain to satisfy demand. The standard operational instinct is to run machinery and personnel as fast as physically possible to maximize utilization rates. Operating without a synchronized pace inevitably leads to overproduction. In lean systems, building products faster than the market consumes them is identified as the most severe systemic waste, tying up capital and masking underlying inefficiencies. Instead of pushing for maximum output, takt time imposes a strict, non-negotiable design constraint on the entire facility's capacity. By enforcing this constraint, operations establish a steady, predictable rhythm that coordinates material flow across entirely different departments, from raw assembly to final packaging. Adopting this metric shifts an organization's focus away from its own internal capability limits and aligns its operations directly with external market realities. To build this operational rhythm, managers must calculate the precise mathematical value of takt time for a given shift. The numerator of this equation is the available production time. This must be the strictly net available time. You must subtract scheduled breaks, routine maintenance, and shift changeovers from gross working hours. The denominator is the customer demand, representing the exact number of units the market requires during that specific time period. This formula acts as the foundation. Takt time equals net available production time divided by customer demand. For a shift with 27,600 available seconds and a demand of 460 pieces, dividing these yields a strict takt time of exactly 60 seconds per unit. This logic applies directly to service environments. If a hospital outpatient clinic has 360 available minutes in a day to see 120 scheduled patients, the calculated takt time is 3 minutes per patient. The formula acts as a universal translator, converting abstract aggregate market demand into a standardized per-unit time constraint regardless of the industry. Once calculated, this single metric becomes the foundational data point for the entire operational system architecture. The resulting takt time serves as the mandatory input for downstream facility design. It dictates line balancing and the physical layout of workstations, ensuring each step of the process is engineered to meet the required pace. It also determines precise staffing levels, allowing managers to calculate the minimum number of operators required for a specific shift. As an operational constraint, takt time has strict characteristics. First, it is purely a time-based metric, never a volume-based production quota. Second, it must remain stable within a set planning horizon to allow workers to standardize their physical movements. Finally, it is calculated completely independently of the factory's current physical capabilities. Takt time functions as the architectural blueprint that forces the internal physical system to mold itself to external market realities. Establishing the required pace of production is only half the equation. Operations must then measure their actual pace of execution against it. The actual, measurable physical time it takes a worker or a machine to complete one single unit is called cycle time. This chart highlights the distinct purposes. Takt time exists to meet customer demand, whereas cycle time is optimized to improve internal efficiency. When these two metrics are mismatched, the system breaks down. If the actual cycle time is greater than the required takt time, the internal operation cannot keep up with the external pace. This specific condition mathematically guarantees the creation of system bottlenecks and results in missed customer orders. In the reverse scenario, where cycle time is less than the takt time, the operation is breaching its external boundary by moving too quickly. Moving faster than the market consumes the product creates overcapacity, forces labor to sit idle, and generates the expensive waste of overproduction. Perfect operational flow is only achieved when the internal cycle time is ruthlessly synchronized to match the external takt time. While it originates on the factory floor, this metric scales directly into macro-level business planning. Takt time integrates deeply into high-level sales and operations planning, translating broad sales forecasts into actionable production rates. It is utilized in capacity planning across massive multi-node global supply chains to ensure different facilities are producing at compatible rates. In non-traditional logistical environments, operations use it to optimize delivery truck routing schedules based on daily volume projections. Service sectors, such as large-scale call centers, apply the same logic to mathematically determine the required staffing levels against projected daily call volumes. Continuous improvement teams use takt time as the ultimate baseline metric for identifying microscopic process deviations and eliminating wasted motion. Across all these sectors, takt time serves as the essential translation layer between executive sales forecasts and frontline operational execution. Maintaining this perfect synchronization requires navigating modern realities that frequently disrupt the system. The primary operational threat to maintaining a stable pace is highly volatile and unpredictable market demand. When order volumes experience rapid, unforeseen shifts, establishing a stable planning horizon becomes nearly impossible, forcing constant recalculations. This instability is further compounded by the modern manufacturing trend toward high product customization and mixed model production runs. Mixed models add significant layers of complexity, requiring engineers to calculate and balance multiple dynamic talk times simultaneously on a single assembly line. Despite these challenges, talk time remains the definitive, demand-driven metronome of lean operations. Operations must calculate their required pace based on net available time and balance actual cycle times strictly against that result. True operational excellence is not achieved by moving as fast as possible, but by moving at the exact speed the market requires.